Welcome to this third video about the preparation of phenethylamines. This video is about CN bond forming strategies. In my channel there's also a video playlist about the preparation of amines by CN bond formation, where you can find a more thorough discussion of the kinetics and other aspects of this reaction. For the preparation of phenethylamines by CN bond formation, the most common electrophiles are phenethyl halides or sulfonates, styrene oxides, and styrenes. Aliphatic alcohols and alkynes can also be used. Typical nucleophiles include ammonia and amines, azide, deprotonated amides and sulfonamides, and nitriles or hydrogen cyanide for Ritter reactions. Aryl ketones can be aminated by intermediate formation of oximes and acyrenes in the so-called Neber rearrangement. When acetophenones are heated with amines and sulfur, thioamides are obtained, which can be reduced to phenethylamines. Ketones can also be nitrosated with nitrous acid or alkyl nitrides and then reduced to aminoketones. I'll show you specific examples in a minute. Let's start with alkylations by phenethyl halides. Alkyl chlorides are often too unreactive, but by treatment with a strong base, 2-hydroxyalkyl chlorides can be converted into epoxides. These are more reactive than unactivated alkyl chlorides and well suited for the alkylation of amines. The rate of such alkylations depends on the concentration of reactants, and to keep the reaction times short, it is important to use as little solvent as possible. Here, an excess of amine was required to prevent twofold alkylation of the primary amino group. 2-hydroxy, alkoxy or aryloxyamines, as the starting and target amines of this example, are less basic and less nucleophilic than simple aliphatic amines. Oxygen is more electronegative than carbon and removes electron density from the amino group through sigma bonds, as discussed in part 2 of this video playlist. Therefore, the amines shown here are difficult to alkylate and to convert into amides by acylation. Alkyl bromides are more reactive than chlorides and well suited for the direct alkylation of amines. In this example, no excess of amine was required, probably because the steric bulk of the amine prevented its twofold alkylation. The unprotected phenol and sulfonamide were not alkylated. Because alkylamines are more nucleophilic than ammonia, the direct alkylation of ammonia usually yields mixtures of secondary and tertiary amines. In this example, however, the continuous reaction of a huge excess of ammonia with phenetyl bromide gave an excellent yield of primary amine. Also here, no secondary amines were formed because of the steric bulk of the secondary alkyl bromide. Moreover, the carboxyl group lowers the basicity and nucleophilicity of the amino group in alpha amino acids. One alternative to the direct alkylation of ammonia is the alkylation of azide. Alkyl acids are easy to reduce to primary amines, for instance by catalytic hydrogenation or by treatment with sulfides, various metals, DMSO, borohydride or phosphines. In this example, mescaline was prepared by conversion of a phenetyl mesylate into an acide and reduction with lithium aluminum hydride. The intermediate phenetyl alcohol was obtained by direct hydroboration of an acetophenone acetal. Some alcohols can be converted into amides by treatment with nitriles and acids in the so-called Ritter reaction. Here, with a mixture of sulfuric acid and sodium cyanide, a tertiary phenetyl alcohol was transformed into a form amide. Alkaline saponification then yielded the amine. Even primary alcohols can be used to alkylate amines, for instance by a one-pot dehydrogenation imine formation reduction sequence. In this example, phenethyl alcohol cleanly alkylated terzbutylamine with the aid of a ruthenium catalyst. Alpha-halogenated aryl ketones, also called phenacyl halides, are more powerful alkylating reagents than simple alkyl halides and do not undergo beta elimination readily. Phenacyl halides can be prepared by halogenating aryl ketones or by Friedel-Crafts acylation with haloacetyl chlorides. In this example, the latter strategy was used to prepare a substituted alpha-chloropropionone. Reaction with an excess of dimethylamine yielded the expected aminoketone. Heating with a diester of tartaric acid for 7 hours led to dynamic kinetic resolution and the formation of mainly one enantiomer of this aminoketone. Enantiomerically enriched aminoketones can also be prepared by alkylating enantiomerically pure amines with racemic enolysable alpha-bromoketones, as shown here. After diastereoselective reduction of the ketone, the amine auxiliary could be hydrogenated off without benzylic deoxygenation or hydrogenation of the naphthalene. The carbon-chlorine bond was also cleaved, but fortunately the amino alcohol could be chlorinated again with the correct regioselectivity. Epoxides are also suitable electrophiles for the preparation of phenethylamines. Styrene oxide mostly reacts with amines at the methylene group, as in this example, because of its better steric accessibility. The benzylic CO bond is weaker because of electron donation by the arene, but steric factors seem to be more important in this case. With a less basic aniline and lithium perchlorate as Lewis acid, however, the regioselectivity could be reversed. Even sterically undemanding amines, like benzylamine, react preferentially with the methylene group of styrene oxide. In this example, a neat mixture of the starting materials was stirred at room temperature for a week, without any solvent. Aromatic ketones like propiophenone can be nitrosated by nitrites under acidic conditions. This reaction is not applicable to methyl ketones, which are oxidized further. But with propiophenone and under optimized conditions, a high yield of oxym can be attained. This is not an easy reaction, because the product readily undergoes acid-catalyzed Beckmann rearrangement. I'll show you some examples when discussing side reactions at the end of this video. In this example, a substituted propiophenone was nitrosated with butyl nitride and hydrogen chloride. Under alkaline conditions, ketones are usually cleaved by alkyl nitrides into oxymes and esters. Catalytic hydrogenation of the alpha-hydroxyaminoketone gave first the aminoketone and then an amino alcohol, without extensive benzylic deoxygenation. Unfortunately, the hydrogenations required hydrochloric acid, what would cause corrosion of most reactors. Thus, for scale-up, some alternative acids would have to be tested. This example is similar to the previous one. Again, the oxym was hydrogenated in the presence of hydrogen chloride, what is difficult to scale up. Examples have also been reported of oxym hydrogenations under alkaline conditions. Here, nitrosated propiophenone was hydrogenated in the presence of sodium hydroxide, and the main product was an amino alcohol. No benzylic CO bond cleavage occurred. An excess of sodium hydroxide would cleave the benzylic CC bond of the starting oxym and should better be avoided. Nitroalkanes are sometimes resistant to hydrogenation. With palladium on charcoal and in the presence of hydrochloric acid, alpha-nitroacetophenone only yielded a nitroalcohol and then nitroethylbenzene. With platinum on charcoal, however, first the aminoketone and then the amino alcohol was formed. A high yield of aminoketone could be attained with a platinum catalyst deactivated by thiourea. Thus, for the optimization of such reductions, it pays to experiment with various catalysts and additives. Heating ketones with iodine and pyridine yields alpha-pyridinium ketones. A related reaction is the direct imidation shown here. With an excess of terz-butyl hydroperoxide as oxidant and catalytic iodide, propiophenone was cleanly converted into an alpha-succinimidyl ketone. Hydrolysis with aqueous hydrochloric acid then gave the alpha-aminoketone. As an alternative, NBS may be used as electrophilic imidating reagent. Propiophenones can also be nitrated at the alpha-methylene group. Like the alpha-nitrosation, this reaction is difficult because of the sensitivity of the product. Nucleophiles can cleave the benzylic CC bond, while treatment with acids can cause Beckmann rearrangement. Anyway, under the optimized conditions shown here, it was possible to obtain a reasonable yield of alpha-nitropropionone. One mild procedure for nitrating ketones is treatment of silyl enol ethers with tetranitromethane. No catalysts were required, and the nitration proceeded at room temperature in dichloromethane. Tetranitromethane can be prepared from anhydrous nitric acid and acetic anhydride, according to an organic synthesis procedure. Unfortunately, this reagent is toxic and potentially explosive when impure, and I would rather choose another nitrating strategy. Alpha-aminoketones can also be prepared by Neber rearrangement of activated oximes. In this example, an oxime was first torsylated and then converted into an azyrene by treatment with potassium ethoxide. Heating with concentrated hydrochloric acid then brought about azyrene hydrolysis to the aminoketone. If the Neber rearrangement is run with a chiral phase transfer catalyst, enantiomerically enriched aminoketones may result. Here, activation of the oxime and cyclization proceeded in one step. No azyrene but a methoxyaziridine was formed in this case. Benzylation and hydrolysis then yielded the final product. Also, azodeicarboxylates can aminate ketones. Here the ketone was further acidified by a carboxyl group. With 10% of a chiral diamine, the amination proceeded enantioselectively. Here a ketone-derived imine was aminated diastereoselectively with an azodeicarboxamide and a slight excess of a strong base. Another method to convert acetophenones into phenethylamines is the Willgerodt-Kindler reaction. When ketones are heated with amines and sulfur, a migration of the carbonyl group occurs and thioamides result. In this example, the starting ketone was prepared by isomerization of acetylated mesitylene. Thioamides can be reduced to amines in several ways. Because a primary amine was the target here, the thioamide was first hydrolyzed to a carboxylic acid, then converted into an amide, and finally reduced with lithium aluminum hydride. As an alternative, thioamides can be activated by methylation and then reduced with sodium borohydride. Catalytic hydrogenation will usually not work because of the strong poisoning effect of the thiocarbonyl group. Here a thioamide was reduced by treatment with a large excess of Raney-nickel. Let's check some examples of the addition of amines to styrenes. Unless the arene is electron deficient, styrenes are weak Michael acceptors and will only react with strong nucleophiles or radicals. Here, lithiated piperidine added to vinyltoluene when air was present. This suggests that radicals might have been involved. At almost 200 degrees Celsius, also aniline could be added to styrene. This reaction was catalyzed by metallic sodium, which converts aniline into sodium anilide. Much milder amination conditions could be realized with a strontium amide as catalyst. No tertiary amines were formed by twofold alkylation of benzylamine. Another suitable catalyst for aminating unactivated styrenes is the ruthenium complex shown here. In the presence of 10% of trifolic acid, an acceptable yield of phenethylamine was obtained after 24 hours at 110 degrees Celsius. Alkynes are more electrophilic than olefins and often react with nucleophiles under mild conditions. In this example, 1% of a titanium amide catalyzed the addition of phenethylamine to phenylacetylene. A mixture of an enamine and an imine resulted, which could be hydrogenated to the final product. Alkynes are formally dehydrated ketones and can also yield thioamides upon reaction with sulfur and amines, as in this example. Acids will convert most styrenes into benzylic carbocations, but allyl arenes can form phenetyl cations. With nitriles, these may undergo a Ritter reaction and yield amides, as shown here. Styrenes can also be nitrated at the vinyl group, but condensation of benzaldehydes with nitroalkanes, as discussed in part 1 of this playlist, is usually a more practical approach to nitrostyrenes. Substituted styrenes are difficult to prepare and to store because of their tendency to polymerize, and benzaldehydes are therefore more convenient starting materials. Here, styrene was nitrated with a mixture of iron nitrate and iron chloride. The chlorinated product could be converted into nitrostyrene by dehydrochlorination with a base. In this example, styrene was transformed into nitroacetophenone by treatment with 2 equivalents of nitrous acid followed by hydrolysis of an intermediate oxime. This here is a rather exotic way of twofold amination of a styrene. First, a sulfonium salt was prepared with a sulfoxide and triflic anhydride. Reaction of this salt with an excess of aniline and potassium terzbutoxide yielded the final diamine. A simpler method would have been chlorination or bromination of the styrene, followed by twofold nucleophilic substitution. Another strategy of aminating styrenes is by treatment with a mixture of an amide and NBS. After reduction of the intermediate aminoketone, a high yield of amido alcohol resulted. The direct oxidative amination of alkanes with nitrines usually yields worthless product mixtures. This here is one of those rare examples where mostly one product was obtained. The nitrine was generated by oxidation of an aryl sulfamate with diacetoxyiodobenzene in the presence of 1% of a rhodium carboxylate. Alpha-oxo-aryl acetamides, like the product of this example, are formed easily by oxidation of ethylarenes. A large number of such reactions have been reported. Here the oxidant was terzbutyl hydroperoxide and 20% of copper iodide. Less common is the direct conversion of alkylarenes into protected phenethylamines shown here. First, a dehydrogenation to a styrene must have occurred, followed by oxidative amidoalkylation, similar to the formation of halohydrines from alkenes. This reaction only succeeded with alkoxyarenes, which are of course easier to dehydrogenate than electron-deficient alkylarenes. Phenethylamines can also be prepared from 2-aryl propionic acids, that is, hydrogenated cinnamic acids. A number of ways have been reported to convert carboxylic acids into amines with loss of one carbon atom. This here is an example of Curtius rearrangement, where an acid is heated with a phosphoryl azide in the presence of an alcohol. Thermal rearrangement of the intermediate acyl azide yielded an isocyanate, which could then react with the alcohol to a carbamate. Mescaline can be prepared by Hofmann rearrangement, as shown here. Treatment of an amide with bromine and sodium hydroxide gave a fair yield of mescaline, without bromination of the arene. This route, however, is longer and less convenient than condensation of the starting aldehyde with nitromethane and reduction. The starting amides for Hofmann rearrangement are best prepared from nitriles. Here, chlorination with a slight excess of hypochlorite yielded a chlorinated amide, which was then rearranged to a protected enamine with sodium hydroxide. This enamine was then hydrogenated to an enantiomerically enriched phenethylamine with a chiral ruthenium catalyst. Let's check potential side reactions. I've shown you some examples of the preparation of phenethylamines from styrenes. Simple amines will usually not add to styrenes under acidic conditions, because protonated amines are not nucleophilic at all. Less basic amines, amides or imides, however, can add to alkenes under acidic conditions. In the case of styrenes, addition will then occur at the benzylic position, as in this example. Anilines can also be alkylated by styrenes at carbon, as shown here. Similarly, aluminum anides react with ethylene to yield 2,6-diethylanilines, without any alkylation at nitrogen. Alpha nitrisation of ketones is difficult because the initially formed oxime readily undergoes Beckmann rearrangement. I've shown you a number of successful examples though, and under optimized conditions it should be possible to nitrosate a given ketone in high yield. Also, alpha nitroketones are sensitive and easy to cleave. Care must be taken during workup to prevent such deacylations. Acids can bring about the Beckmann rearrangement of nitroketones, which yields N-hydroxyimides. Alpha-aminoketones can easily decompose or oligomerize. Cyclocondensation, for instance, yields dihydropyracenes or, after dehydrogenation, pyracenes. Aminoketones can also rearrange by intermediate formation of iminoalcohols. Heating this aminoketone to 240 degrees Celsius, for instance, led to a scrambling of the phenyl and ethyl groups. Here are some further references which you can also find in the description of this video. Under the Community tab of my channel there's a PDF version of the slides. This was the last video of this playlist. Hope you found it useful. If you have ideas for new videos, just let me know in the comments. Some of you already came up with good ideas, what I really appreciate. And thanks for watching.